Professor William Schneider from the University of Notre Dame. To give you a little bit of background on Professor Schneider, he's in the Department of Chemical and Biomolecular Engineering and also Department of Chemistry and Biochemistry. He's the principal investigator on the GSEP effort titled Chemically Complexing Ionic Liquids for Pre-Combustion CO2 Capture. His expertise is in chemical applications of density functional theory simulations. And at Notre Dame, he has continued his research into the theory and molecular simulation of heterogeneous catalysis, with a particular emphasis on reaction environment effects on catalytic materials and their implications for mechanism and reactivity. Schneider was recently recognized as a fellow of the American Association for the Advancement of Science, and he's co-authored more than 110 papers and book chapters.
Jen, thank you for the introduction. It's my pleasure to be here to represent the project that we're just starting at Notre Dame. Actually, our start date was just 10 days ago. So we're very pleased to have the funding and to have the opportunity here to talk about what we plan to do. So this session is about carbon capture and CO2 separations. And not knowing what the audience was going to be, I thought that I would do a very simple introduction to some of the basic ideas surrounding separations. So the idea that we're all trying to work on is to take a gas, it's a mixture of molecules, here red and blue balls, and separate them into two fluids that are separate from one another. And thermodynamics teaches us that there's an intrinsic, unavoidable work associated with doing that separation. And if you take two gases at say 50 degrees or so, that works out to be about 2 kilojoules per mole of material. And if you apply that factor to the amount of gas that's coming out of a coal-fired power plant, that translates into about 40 megawatts of work necessary at a minimum to separate the gases that are coming out of a power plant. Now, in order to accomplish that separation, you need a machine to take those materials apart. And I mean a machine in a very kind of loose general sense. One of the most common machines is an absorbent that selectively binds one of the species over the other. So if I start this little movie here, you'll see that I've put our gas mixture in contact with an absorbent that's selective for the red component. And now to effect a separation, I have to take those two phases away from one another and then allow the phase that's saturated with the red molecules to then desorb those molecules. And so my machine is that absorbent that's driving this separation back and forth, and to be a machine it has to work in a cyclic fashion. Now the energy that I gave you on the previous slide is a minimum. In general, any real machine is going to cost more, in general a lot more than the minimum in order to effect the separation. And that energy cost is going to depend exactly on how that machine or material or absorbent works. So let me give you a real simple example. Let's imagine that our machine is a liquid absorbent, and let's imagine that we're going to separate CO2 using that liquid absorbent. And even further, let's assume that the absorbent follows a Langmuir isotherm. So this is really hard to do without being able to point. But the notion is that the absorbent combines chemically with the CO2 to make a product in the condensed phase. The interaction between that gas and the absorbent is defined by an isotherm. And that's these curved lines here. So now imagine that I'm going to do a gas separation. I'm going to bring a gas in contact with this absorbent at some, say, low temperature represented by the blue line, and at some nominal pressure of the gas. And so the fluid will take up some amount of the gas represented by the intersection of the blue line with the y-axis. Now I'm going to take these materials apart, and I'm going to do something to drive the gas back out. Say I'm going to pull a vacuum on it, or in this example, I'm going to heat it up. And so now the solubility of the gas in that absorbent is going to diminish, and so I'll have a new composition that's down here. A very crude figure of merit for this absorbent is that delta between the capacity that it had when it absorbed the CO2 and the capacity that it had when it desorbed it. Now, what's controlling the shape of these isotherms? Well, largely what's controlling it is the binding energy of my gas, whatever I'm trying to draw into that absorbent, with the absorbent phase. And that is, in this particular example, where I'm reacting with CO2, it's the bond energy of the CO2 with the absorbent. So that's a parameter that one can adjust. Oh, can I pause for a moment? Oh, that would be much easier. So I have a 4-year-old, and when she wants a break in a game, she says, pause game. So pause game. All right. Now we're back on. Oh, that's much. Now I can get out from much, much better. Okay, so as I say, the kind of the fundamental descriptor here is the binding energy of the absorbent for CO2. If that binding energy is very strong, you'll be very effective at taking up CO2. You'll do a very poor job of giving it up at this kind of fixed condition that I'm saying that we're going to desorb at. So you won't have a very effective machine for doing your separation. By the same token, if your absorbent binds the thing that you're trying to remove, CO2 in this case, very weakly, it will neither take it up it will give it up very easily, but won't take it up very effectively. And based on these very simple arguments, you can easily imagine that there's a volcano curve that represents the efficiency of the separation, that this delta mole ratio is a function of the binding energy. I do all this simply to motivate the idea that if we want to design a material that's going to be a selective absorbent for CO2 and use it for a particular application, one thing that we must have good control over is the binding energy of the absorbent for the carbon dioxide. The arguments that I've made are highly qualitative, and so I wouldn't even put units on here because the exact units, the exact numbers depend on the application, but the idea holds. All right. So now we're here largely to talk about CO2 separations, and so I'll remind you that there are already many different types of materials that are being used or proposed to be used to do CO2 separations, absorbents that are selective for CO2. Aqueous amines are the most common of those. This is really not working very well. They have a particular chemistry with CO2, a particular reactivity by which they take up and give up CO2. And there are other types of absorbents. The details don't matter. All of these have shortcomings. Some of those shortcomings are related to the complexity of the chemistry that's involved in the uptake of the CO2 and the absorbent, the rates of reaction, and really the most critically, the matching of the thermodynamics and the properties of those materials to a particular separation. They're not well matched, and so the cost of running these separations is quite a bit higher than the ideal that I mentioned before. We've been interested for a number of years in using what are called room temperature ionic liquids as absorbents for CO2 separations. And there's a couple good reasons for that. Ionic liquids are a class of fluids that have reasonably good affinity for CO2 relative to other gases that one might want to do separations against, like oxygen and nitrogen in this plot. So these are isotherms like I've shown you before. More importantly than that, they have negligible volatility and highly tunable chemistry. Now, the kind of base level ionic liquids that one might find, say from Aldrich or such, have fairly low capacities for CO2. So 10 years, or actually more than 10 years ago, people hit on the idea of developing chemically functionalized ionic liquids, materials with functional groups in them that react selectively with CO2 to make products. Here's our delta H of reaction, and now a separation can be run by driving this reaction forward and backwards in the absorbent. Let me take a step back for a second, and for those of you who aren't familiar, and just let me say what ionic liquids are. So these are salts, like sodium chloride is a salt, composed of cations and anions, but the cations and anions are large, bulky species, so that they don't pack very well. And as a consequence, the melting point of the salt is subambient. So they're actual liquids at room temperature. But again, because they're ionic, they have no volatility. You can pull a vacuum on them, you can do UHV on them, and they don't volatilize. Further, you can imagine almost an infinite number of ionic liquids. There's very, very many anions, or cations one can imagine, very many anions one could imagine, and put any two of these together, which is done very easily, and you have a new ionic liquid. So this is our platform for doing our CO2 separations. Now, this great versatility, or great diversity in materials is a boon for us. It's also a bit of a problem for us, because now you're going to go into the laboratory and design an ionic liquid to do a separation, but what do you choose? So my group and Ed McGinn's group at Notre Dame, we collaborate together on this project, are expert in using molecular level simulations to probe the properties of materials. My group does ab initio calculations that are suitable to calculating binding and chemical reactivity. Ed's group does classical simulations appropriate to studying the physical properties of materials. And put those two together and you have a predictive platform for driving the discovery of new materials. We've been working on these ideas for 4 or 5 years or so now, 5 I guess. And one of the first things that we tackled, so we wanted to think about this idea of designing an ionic liquid with a functional group to capture CO2. And one very obvious degree of freedom is, well, if I'm going to put a functional group on my material, should I put it on my cation or my anion? Very simple decision. So or question. So we did some calculations, some first principles calculations that led us to believe that while everybody else largely had been putting functional groups on the cation, there was substantial benefit to be had by putting them on the anion. So Joan Brennecke, another collaborator on this project, went into the laboratory, synthesized a couple ionic liquids with amines on the anion, and recovered these isotherms here. And I don't want to belabor the details, except to say that this performance was much better than what had been seen with ionic liquids before. And not only that, the relative binding strengths, which are buried in the slopes of those isotherms, are exactly what were predicted from the simulation. So it was a very nice success, both from the theory perspective and the experimental perspective. We can do things like spectroscopy to confirm that what's happening is what we think is happening, and it is. Now, there are problems with that particular chemistry, which we called our Generation 2 ionic liquids. It was relying on a chemistry very much akin to the monoethanolamine chemistry, which is kind of complicated and hard to control. And there were also big changes in the physical characteristics of the ionic liquid when they were exposed to CO2. Specifically, they became very viscous because of the generation of hydrogen bonding networks in the reaction products. So we sat down and wrote down a few design targets for what we'd want in an optimized ionic liquid for CO2 capture. We decided that we wanted it to be anion functionalized, that we wanted it to have no potential for creating hydrogen bonds, so we wanted it to be aprotic. We really want to have this tunability built right into it, and we want the kinetics to be as clean and reversible as possible. And we tossed around a lot of ideas before we hit on the notion of what we call aprotic heterocyclic anions, or AHAs. And these are anions, like these here, that are intrinsically Lewis basic because of the hetero atoms that are in it. And as I say, they're anionic, so potentially one could make ionic liquids out of them. The first thing we did was turn to the computer and see whether these AHAs, as we call them, would react with CO2. And I think I'm supposed to click something, and I don't know. Let's see if this... see, that's what happens in moving it to another computer. You don't get to see the little movie of the CO2 binding to the... yep, see, it's not going to work. So what should have happened was that CO2 should have come down and landed on top of here and created a bond. So that tells us that this anion has a potential for being a CO2 capture agent. Further, the platform we predicted from the calculations would be highly tunable by introducing functional groups onto this heterocycle ring. What we found is that we should be able to tune the binding energy of the CO2 to the anion over a wide range. Of course, the proof is in the pudding. After we did these calculations, Joan went into the laboratory, Joan's students, and synthesized one of these AHAs. The first good news was that they could actually be synthesized, so we did get ionic liquids out of these materials. She did CO2 uptake isotherms on them. They're exactly what one would expect based on what the calculations said they should be. And further, the most significant thing really was that this viscosity problem that we'd had before disappeared, exactly like we expected because we designed the protons out of the problem. So this is our platform, this AHA platform for a tailorable CO2 capture material. You can very easily on the computer go and test other anions, put nitrogens in different places on the heterocycle ring, conjugate or fuse the ring to another ring, put substituent groups on it. The only point I want to make is that the prediction is that we should be able to get binding energies that go all over the place. And that's exactly what we want. Further, Joan has, since that first report, gone and synthesized actually many more than are represented here. But these are isotherms of ionic liquids, all of this same class, this same general type, but different in detail. And the point is that the binding energies go all over the place, so the uptake is highly tunable just by changing this anion. Exactly what we were hoping for. This research that we conducted under grant from Notre, the Department of Energy, has spawned a number of different projects. Based on these ideas, we've developed actually an air conditioning concept based on this same idea of absorbing and desorbing CO2 from a liquid phase. It's an alternative to a transcritical CO2 cycle. We've developed what we call phase change ionic liquids that do this separation in combination with a phase change between a solid and a liquid state. We're working on using these for actinide separations, and most germane to this discussion, through some seed funding that we had through Notre Dame, we've developed some ideas that could be useful for pre-combustion CO2 separations. And that's the genesis of this Stanford project that, as I say, is just starting a week or so ago, last week, I guess. So in the GCEP project, which, as I say, we are just starting on, we are going to focus on pre-combustion CO2 separations. Everything that we've done to this point has really been informed by thinking about post-combustion. Pre-combustion is different in a number of important ways. For one thing, we're going to be separating CO2 from hydrogen rather than CO2 from nitrogen and CO2 from water and such. The nominal temperatures and pressures that one needs to deal with are different than one would be dealing with when doing post-combustion. The amount of gas that we're going to have to deal with is much less, so that's a good thing from our perspective. And so what we're going to do underneath this is really an extension of what we've done already. That is a model-driven materials development framework in which we use simulations to guide the design of new materials and then controlled synthesis and characterization of those materials. We, in particular, are interested in building on some ideas of designing in cooperativity to improve the performance of improve the energy efficiency of the separations. Here is a photo of the GCEP team. We had our kickoff meeting just a few days ago. You'll see yours truly in there. Joan Brennecke is the principal investigator on the project. Ed McGinn, Brandon Ashfeld, Mark Stodhair, and associated members of the research group. So we have a very nice team. We're very excited about working on this. Very thankful to GCEP and all the funding companies for providing us this opportunity to extend the work that we've been doing. So I must be out of time. No? All right, so I'll show my last slide. I can't help, since being here at Stanford, to make the point that our two fine institutions are going to meet on the battlefield in South Bend in just a couple days. I have to fly out Friday to be home in time to see the football game, go to the football game, and so just so we're clear on the, don't spoil our season, that's all I'm saying. And I'll end with this. We have a famous saying at Notre Dame, and so I modified a little bit, GSEP, like a champion today. Thank you for the invitation to speak with you. I'd be happy to answer any questions.
Typical way of cycling these things is pressure cycling or temperature cycling. Correct. Or some combination of the two.
Right.
But you have to wonder if there are other possibilities, particularly with the ionic liquids. I mean, what happens when you change the voltage across? Is there any potential for electrical cycling of these things? And if you could, without having to move lots of charge, it might be an interesting approach.
Yeah, we haven't really looked at electrochemical. So the ionic liquids are terrible electrical conductors. They're good ionic conductors, but they're horrid. They're insulators, electrical insulators. So okay, so maybe that could. We've thought a little bit more about doing photochemical. So designing it, because you have a heterocycle, you have potentially a chromophore there, especially if you build some conjugation into it. So we've done some work in looking at doing photo-driven CO2 separation. So yeah, I think there are other other approaches. When you think about this, if you really want to do CO2 separations on a power plant, there are practical constraints on what you can do, and one of the things we've argued is that liquids are convenient and thermal cycling is convenient just because we really know how to do it very well. But we are thinking about other types of ideas like that.
Hi. So these heterocyclic compounds are aprotic, but the environment that they're going to be used in is often going to have a lot of moisture around.
Indeed.
So how does the presence of moisture affect that? Does it complicate it or
Indeed, it does complicate it. The answer actually depends on the exact material, and so that was a detail I wasn't going to get into. We got lucky. The first material that we published on, apparently, so they all take up water to some extent. The first material that we published on actually does not react with water, and so it doesn't interfere with the CO2 uptake at all. And but there are others of them, particularly ones that are stronger bases that can also have some interfering chemistry with water. My sense is for the pre-combustion, that's going to be less of an issue than it is for the post-combustion. In fact, in the application to the post-combustion that we've been looking at with these phase change materials, the idea that we're proposing is actually to do a dehydration is the word that's coming to mind, but I don't think that's the right term. But to drop the water out of the gas before putting it into the separator. And our energy analysis indicates that that's actually a plausible thing to do. I mean, if you grant that any of this is plausible, it's a plausible thing. But the bottom line is, yes, you're right. The water is a complication that we need to worry about.
to that? These heterocyclic compounds you talked about were monofunctional. Can you actually make ones that have like difunctionality? There's two groups that would
You can. So the simplest thing, so some of these had multiple heteroatoms on them. Unfortunately, the first binding deactivates the ring, and so you don't get multiple uptake in the simplest way that one might imagine. But again, we're working on some ideas where we might design in a little bit more clever way some allosteric type behavior where one CO2 might drive the binding of a second.
From an efficiency point of view, would it help to design these liquids which, with a very small temperature change, go from a very large absorption amount
Indeed.
to negligible amount?
Indeed.
And are you in the process of working on something like that?
So that's what I mean by cooperativity. So if you, what you're suggesting, I think I'm unplugged. So my isotherms looked Langmuirian, and Jones' isotherms looked Langmuirian. And that's because what that means fundamentally is that each CO2 is binding independent of any other. They're ignorant of one another. But if those CO2s knew something about one another, then you would have a cooperative system. Your isotherm would start to look sigmoidal. And so if you could design that in, yes, you could have a much more efficient separation. Right now, that's a concept without a demonstration, but we're working on it.
Thanks. My little sense of ionic liquids is that they're exorbitantly expensive to actually synthesize and make. What's your sense of this in terms of what you're working on and overall the overall production of the liquids once you do find a formulation that is very attractive?
Right. Well, certainly if you go to a catalog and buy an ionic liquid off the shelf today, they're expensive. Like anything that's made is kind of a one-off thing, they're expensive. The thing to bear in mind is that there's nothing intrinsic in the ionic liquids that make them expensive. It's just that they're not made in any sort of large volume. So we don't see any. It's never good. An ionic liquid is never going to be as cheap as aqueous ammonia, for instance, but it doesn't necessarily have to be at the cost that it is today. In the cost estimations that we did for the Notre project, we used a cost estimate of $10 a kilogram, which through some estimation we figured was a reasonable number to use given the volumes we expected we would be using. And based on that and the rate of decomposition of the things, you get the materials costs are quite manageable. So, I mean, in a way, the chemistry is very nice. To make an ionic liquid is an easy thing. So it really comes down to the cost of these components, and it's a question of how clever you can be in building those components.
I wonder whether there's anything to be taken away from some sort of a biomimetic strategy, since nature has already invented a very good cooperative CO2 binding substance called hemoglobin.
Yeah. Is that, so hemoglobin cooperatively binds oxygen. Does it cooperatively bind CO2
Yes.
as well? All right.
And it binds it with the amino terminal residue, which is a charged component.
Right.
So
Well, in fact, if you think about the porphyrin ring in hemoglobin, it's 4 of these fused heterocycles, right?
True.
So, yeah, so I think that, yeah, so we've thought of these general ideas. I guess I didn't appreciate that hemoglobin was cooperative for CO2 as well.
cooperative with CO2 and oxygen in a
Right, so it's
reversible way.
right, so certainly for oxygen, yeah, and so that's the kind of the motivation of thinking about these cooperativity ideas at all. But yeah, it's designing something. Of course, Mother Nature does it very well on a very small scale and without much consideration to.
And has had a very long time to do.
And has indeed.
I just have a quick question for you myself.
Uh-huh.
What is the application of the material? Are you thinking of a packed tower? And if so, how do the viscosity and the surface tensions compare to, say, amines or sodium hydroxide?
Yeah, so the viscosities are certainly higher. So you're actually talking to the wrong person about the details of the engineering. But we have columns in the laboratory that we're running. The ionic liquid flows down. Contacting the liquid with CO2 is not a particularly big problem. The viscosities do vary a lot. I touched on that a little bit in my talk. And so one of the things that we're working on is strategies for controlling the viscosity. Of course, you change the viscosity, sometimes you screw up the CO2 absorption properties. It's a multidimensional design problem. A good question.
Thank you very much.
Sure.